Picture this. You are standing in the dark. Not just any dark, but the deepest dark you've ever known. And somewhere above you, 26,000 light years away, embedded in a dense, golden smear of ancient starlight, something is waking up. You can't see it. You can't feel it. You have no way of knowing. But right now, at the center of your own galaxy, a monster the mass of 4 million suns is stirring, flashing, erupting, not once or twice a day, but constantly, over and over again, without pause, without pattern, without rest. And until very recently, we had absolutely no idea. This is the story of Sagittarius A*, the supermassive black hole at the heart of the Milky Way, and why everything we thought we knew about it turns out to have been wrong. From a distance, our galaxy's center doesn't look dangerous. If you could step outside the Milky Way and gaze inward, you would see a soft, radiant core, warm and golden, like embers at the base of a fire. Beautiful, even serene. 100 billion stars packed so densely together that their combined light blurs into a single luminous mass. But at the precise center of that glow, something else entirely is waiting. Sagittarius A*, or Sgr A*, pronounced Sagittarius, is a supermassive black hole with a mass equal to roughly 4.3 million of our suns. Its event horizon, the boundary beyond which nothing can return, spans about 24 million kilometers across, roughly 17 times the diameter of the Sun. And yet, in cosmic terms, it is remarkably compact. So small, so far, that from Earth it would appear to occupy the same patch of sky as a donut sitting on the surface of the moon. That's worth sitting with for a moment. The black hole at the center of your galaxy, for million suns worth of mass, compacted into a region not much wider than our tiny corner of the solar system, 26,000 light years away. Not in another galaxy, not in some unimaginably remote corner of the universe. Right here, at the center of the structure you live in, closer to you than the stars of the outer arms of the Milky Way. For most of modern astronomy, this object was considered quiet, almost docile by black hole standards, a sleeping giant. The operative word being was. Astronomers first identified Sagittarius A*, in 1974, when Bruce Ballack and Robert L. Brown detected an unusually bright compact radio source at the exact center of the galaxy, one that refused to be explained by any ordinary stellar process. But confirming what that object truly was would take decades. The key came from an extraordinary act of patience. A team of astronomers, led independently by Reinhard Genzel in Germany and Andrea Ghez in the United States, spent years tracking the movements of individual stars in the immediate vicinity of the galactic center, through the dust, through the interference, through thousands of hours of painstaking observation. What they found was stunning. The star known as S2 and others nearby were observed orbiting Sagittarius A*, and from examining S2's orbit, the team determined the mass of Sagittarius A*, to be 4.1 million solar masses, confined in a volume no bigger than our own solar system. Only one thing in physics can achieve that ratio of mass to volume: a black hole. For this discovery, Genzel and Ghez shared the Nobel Prize in Physics in 2020. The monster at the center of our galaxy was real, confirmed, named. And then, in May 2022, humanity crossed another threshold. The Event Horizon Telescope collaboration, using a worldwide network of radio telescopes functioning as a single Earth-sized virtual instrument, unveiled the first direct image of Sagittarius A*. That image, a glowing ring of hot gas surrounding a dark central shadow, was more than a photograph. It was the first time human eyes had ever directly witnessed the boundary of a black hole in the heart of our own galaxy, a threshold between the known universe and something our physics still cannot fully describe. And what that image showed was a black hole that appeared, more or less, to be sitting still, quiet, stable, manageable. That turned out to be an illusion. To understand what we now know, you have to understand what it means for a black hole to accrete, to feed. Most of the material that could fall into Sagittarius A asterisk never does, at least not directly. Instead, it settles into a swirling structure surrounding the event horizon called an accretion disk, a flat ring of superheated gas and dust that orbits the black hole, heating to millions of degrees through the sheer violence of compression and friction. As material in this disk slowly spirals inward, it radiates, it emits light, X-rays, radio waves, infrared. And when conditions in the disk become particularly turbulent, it flares. On average, Sgr asterisk accretes material at a very low rate. That sounds meager, and by active galactic standards, it is. Some supermassive black holes consume entire star systems worth of material every single year, blazing with the power of trillions of suns, visible from halfway across the observable universe. Those are quasars, the brightest persistent objects in existence. Compared to them, Sgr A asterisk was seen as a ghost, a faint whisper, a black hole that had run out of lunch. But that characterization, as we now know, was dangerously incomplete. It is always bubbling with activity and never seems to reach a steady state. That is not a metaphor. That is a direct quote from a scientist who has been watching it most closely, and what he found, with the help of the most powerful space telescope ever built, genuinely shocked the astronomical community. In February 2025, a team led by Dr. Farhad Yousefzadeh of Northwestern University published their findings in the Astrophysical Journal Letters, and those findings rewrote the picture. The team used NASA's James Webb Space Telescope to observe Sagittarius A asterisk for a total of 48 hours, in 8 to 10 hour increments across 1 year, across 2023 and 2024. They wanted to track how the black hole changed over time. What they expected was occasional flaring, temporary bursts of brightness, the kind of thing that had been documented before in other black holes. What they found was something else entirely. The accretion disk surrounding the black hole generated 5 to 6 big flares per day, and several small subflares in between. Not occasionally, not once a week. 5 to 6 significant eruptions every single day, without a single period of rest. While some flares are faint flickers lasting mere seconds, other flares are blindingly bright eruptions that spew daily. There are also even fainter flickers that surge for months at a time. The levels of activity stretched from bursts that lasted a few seconds, all the way to prolonged brightening events that persisted across months. We couldn't find a pattern in this activity. It appears to be random. The activity profile of the black hole was new and exciting every time that we looked at it. Random, constant, unpredictable. In 48 hours of observation, there was not a single moment of stillness. Now, what is actually happening at the edge of that event horizon? Scientists believe two distinct processes are at work, operating at different scales and timescales, like two different instruments playing simultaneously in the same orchestra. The first process involves minor turbulence within the accretion disk itself. Turbulent fluctuations within the disk can compress plasma, a hot, electrically charged gas, to cause a temporary burst of radiation. These are the faint flickers, the small ripples in what is already an extraordinarily violent river of material. The second process is far more dramatic. Magnetic reconnection events produce hotspots, dense clumps near the event horizon that generate brief, intense flares. Magnetic reconnection, the same phenomenon that drives solar flares on our own sun, occurs when opposing magnetic field lines snap and rejoin, releasing enormous amounts of energy almost instantaneously. Except near Sgr A asterisk, the energy scales involved are incomparably greater, and the frequency is relentless. Here is what makes this discovery particularly unsettling. The flares and flickers varied in brightness and duration, with the brightness changing from hours to minutes to seconds. At the shorter wavelength of observation, brightness changes occurred just slightly before the longer wavelength signal. This was the first time scientists had seen a time delay in measurements at these wavelengths. The longer wavelength lagging behind the shorter one by a very small amount, maybe a few seconds. That delay is a clue, a fingerprint, evidence that different processes are occurring at different distances from the event horizon itself, like layers of an explosion, unfolding in sequence. And the brightest flares, the ones that appear like sudden blinding eruptions before quieting again, are believed to originate from a region so close to the event horizon that the gas completing a single orbit there moves at a significant fraction of the speed of light. The universe's most extreme racetrack, and the laps are measured in minutes. But this is not the first time Sagittarius A asterisk surprised us. There is an earlier chapter in the story, one that carries its own unsettling lesson about what this black hole is capable of. In 2011, astronomers detected something unusual falling toward the galactic center. A compact object, later called G2, appeared to be a small cloud of gas, roughly 3 Earth masses worth of material, locked onto a near radial orbit aimed almost directly at the black hole. The anticipation in the scientific community was enormous. Predictions circulated of a dramatic feeding event, a sudden brightening as the cloud impacted the hot gas surrounding Sgr A asterisk, a flare that would be visible across the electromagnetic spectrum. Some astronomers compared it to watching a comet fall directly into the sun, magnified by millions. 2014 arrived. The world watched. Nothing. G2, whatever it truly was, survived the encounter. It passed within a distance of roughly 260 Australian dollars from the event horizon and emerged on the other side stretched, deformed, but largely intact. What astronomers had assumed was a simple gas cloud turned out to be something more complex, and the black hole, for all its gravity, could not entirely swallow it. The lesson was stark. Sagittarius A asterisk is not the indiscriminate devourer that popular imagination suggests. It is selective, inefficient, in many ways more mysterious for what it does not consume than for what it does. And yet, it is clearly not asleep. That 2014 passage may have contributed additional material to the accretion disk, a slow-release feeding that doesn't produce the sudden dramatic burst we expected, but instead gradually stokes the nonstop burning that JWST has now documented. The black hole is not simply reacting to what falls into it today. It carries the memory of its past meals in the structure of the gas that surrounds it. In March 2024, the Event Horizon Telescope released something new. Not another image of the shadow, but an image of Sgr A asterisk seen in polarized light for the very first time. What polarization reveals is the geometry of magnetic fields, and what astronomers found was striking. Strong and organized magnetic fields spiraling from the edge of Sagittarius A asterisk, with a structure strikingly similar to that of the black hole at the center of the M87 galaxy, suggesting that strong magnetic fields may be common to all black holes. This similarity also hints, tantalizing and not yet confirmed, at something hidden inside Sgr A asterisk, a jet, a directed beam of relativistic plasma, the kind that the M87 black hole launches with extraordinary violence across hundreds of thousands of light years. If Sgr A asterisk harbors a hidden jet, it would have profound implications for the evolution of the Milky Way itself. Jets like these, in other galaxies, have been observed shaping the birth and death of entire stellar populations. They are not merely local events. They are galactic-scale forces. Whether our black hole has such a jet remains unknown. The magnetic field structure suggests it might. The observations so far are consistent with it. But confirmation requires a resolution we do not yet have. The Next Generation Event Horizon Telescope, the ENIAC, is already underway. Its goals are extraordinary. The ENIAC will capture real-time black hole movies and produce the sharpest ever images of black holes. It will test Einstein's general theory of relativity at the event horizon, in the most dangerous relativistic laboratory in the universe. It will uncover the nature of the magnetic field, the unseen force that shapes the surroundings of black holes. It will discover the origin of black hole jets, the immense beams of particles that defy a black hole's gravity. Movies, not photographs. Movies. During the course of one night of observing Sagittarius A asterisk, you may see 8 or 9 orbits of material around that black hole. The ENIAC is being designed to capture that motion, to render the swirling of plasma around an event horizon into something we can actually watch unfold. Meanwhile, Dr. Yusuf Zadeh's team has submitted a proposal to observe Sgr A asterisk with JWST for an uninterrupted 24 hours, twice as long as any previous session. The goal: to reduce noise enough to see whether the flares follow any hidden periodicity, any rhythm buried beneath the apparent randomness. That answer, if it comes, will be fundamental. A random black hole is one kind of object. A periodic one that pulses on a hidden clock, is something else entirely. It could constrain the spin rate of the black hole. It could reveal the geometry of the accretion disk at scales we've never probed. It could, in a very real sense, give us a heartbeat. So here is where we stand. At the center of the galaxy you inhabit, 26,000 light years from the planet where you are sitting right now, there's an object with a mass of 4 million suns, surrounded by a disk of plasma heated to millions of degrees, erupting with major flares 5 to 6 times a day, flickering constantly between eruptions, carrying the imprint of gas clouds and stellar encounters that occurred thousands of years ago, and possibly hiding a jet that could one day influence star formation across the entire Milky Way. It is not awakening. It was never truly asleep. We were simply not watching closely enough. Consider the light you're looking at right now. The photons reaching your eyes traveled from your screen in nanoseconds. The light from Sagittarius A asterisk, if it could reach you directly through the dust and gas of the galactic plane, would have left the galactic center 26,000 years ago. The flares that JWST observed in 2023 and 2024 actually erupted when your ancestors were painting caves on the walls of a world that had never heard a human language. The black hole you are now learning about has been doing this for longer than human civilization has existed, and we are only now, in this moment, beginning to see it. There is something humbling in that, something that resists easy resolution. A black hole does not know you are watching. It does not change its behavior for the telescope. It does not slow its flaring or quiet its accretion disk out of courtesy. It simply is burning, erupting, consuming, releasing. Following rules of physics we have only partially decoded, in a place we will never physically reach, doing things we are only now beginning to measure. And the deepest question, the one that no telescope has yet answered, is not whether Sagittarius A asterisk is active. We know it is. The question is, what, exactly, is it building toward? I hope this gave you a new perspective on the black hole at the center of our galaxy. If you enjoyed it, consider subscribing. See you in the next one.